Okay, so we're recording now. This is example 5 from the presentation, which is propagating the uncertainty in the gravitational constant based on the formula for a pendulum. And so the formula that you were given was the gravitational constant equals 4 pi squared times the length of the pendulum divided by the period of the pendulum squared. And so basically you have this pendulum, the length of the string that this mass is tied to is L. And basically the pendulum swings back and forth, and the period, the period of swinging back and forth one time is T. Okay, and you were told that, let's see, L equals 92.95 plus or minus 0.1 centimeters, and T was 1.936 plus or minus 0.004 seconds. Okay, so basically this formula involves a quotient between two unknowns. So we could replace this formula with G equals A over B, where A would equal 4 pi squared L, and B would equal T squared. Okay, so first we can calculate the best value for A and the uncertainty in A. So the best value for A is just going to equal 4 pi squared times the best value for L. And that is equal to 4 pi squared times 92. Let me make this a little bit neater. 92.95 centimeters. Let me make this a little bit thicker, then maybe it'll work better. Okay, and if you punch this in your calculator, you should get a value of A best equals 3,669.51 centimeters. Okay, and delta A then, so A is just a constant, right? 4 pi is an exact constant, it's an exact number times L. So delta A is just going to be that exact constant, 4 pi squared. This is not wanting to write, 4 pi squared times delta L. Okay, and that is equal to, so we take 4 pi squared times 0.1 centimeters, and the result is going to be 3.9 centimeters. Okay, so what about B? Well, B is equal to T squared. So B best is going to be just the value of T best, so 1.936 seconds squared. This is in units of seconds. So that's going to equal 3.748 seconds squared. And how about the uncertainty in B? Well, the uncertainty in B, based on the formula for raising something to an exact exponent, that's just going to be the absolute value of the exponent times the uncertainty in the value over the value. And sorry, this should be delta B over B best. Right, so the relative uncertainty, the fractional uncertainty in B is equal to this quantity here. Okay, so delta B then we would get by taking B best, right? We multiply both sides by B best, which is 3.748 seconds squared, times the absolute value of the exponent, which is 2, times delta T, which was 0.004 seconds, divide by 1.936 seconds. Okay, and if you punch that into a calculator, you should get 0.015 seconds squared. Okay, so how do I get a new page? Okay, so I'll go to a new page and we'll look at then the final result. So we calculated the uncertainty in the numerator and the uncertainty in the denominator, but we still need to calculate the gravitational constant G and its uncertainty, so delta G. So delta G equals A best, A best over B best, which was equal to, A was 3669.51 centimeters. Divide by B best was up here 3.748 seconds squared. Okay, and so that is equal to, let me see, that should be 979.06 centimeters per second squared. Okay, and what about the uncertainty then? Well, for the uncertainty, we just use this product for quotients. I'm sorry, the equation for quotients. So delta G over G is equal to, it's going to be equal to the square root. Whoops, I changed color. Okay, here we go. Delta A over A, quantity squared, plus delta of B over B, quantity squared. Okay, and so if we then plug in the numbers, delta G equals G best, which is 979.06. And the units are going to be centimeters per second squared times the square root of 3.9 centimeters divided by 3669.51 centimeters quantity squared, plus delta B was 0.015 seconds squared, divided by B best was 3.748 seconds squared, and then quantity squared. Okay, and then if you calculate that, you should get 4.05 centimeters per second squared. Okay, so if you were writing a lab report where you were reporting the gravitational constant, how would you write it? Well, you would write G equals 979. And so the uncertainty in delta G is in the ones digit place. So you're going to round G to the nearest ones digit place. So you're just going to round to 979. Plus or minus, you're going to round the uncertainty to just one significant figure. So plus or minus 4. And the units are centimeters per second squared. You might be more familiar with this number in units of meters per second squared. So if you want to convert to meters per second squared, just divide by 100 centimeters per meter, and you'll get 9.79 meters per second squared. And the number, oh, I'm sorry, I forgot the uncertainty. 9.79 plus or minus 0.04 meters per second squared. Okay, and the number you might be familiar with from your physics textbook is 9.81 meters per second squared. So to within the uncertainty, it looks like this experiment was successful. Okay, any questions about that? Okay, let's see. I want this guy. Okay. Okay, so this was a bit tedious, right? This took us a little while to calculate this uncertainty. So there's an easier way to do it. So you don't have to do this step-by-step procedure. There's a general formula for error propagation if you have a function of multiple variables. So if you suppose that x, y, z, etc., are measured values with uncertainty, delta x, delta y, delta z, and so forth, and you're calculating some function, it's a function of more than one variable, q of x, y, z, dot, 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 then the uncertainty in q is given by this formula. So for each independent variable that has uncertainty, you take the partial derivative of q with respect to that variable, holding all the other variables constant, you multiply by the uncertainty in that variable, and then you square this whole term here. And then you got one term under the square root sign for every independent variable that has an error associated with it. Okay, so all of the formulas that we've used so far, you could derive just from this one formula. This is the only one that you would have to memorize. Okay, so in the next example, we're going to use the general formula to find this gravitational constant and its uncertainty. In order to apply this formula, the assumption is that the given uncertainties are independent and random. Okay, so again, we have G equals 4 pi squared, 4 pi squared L over T squared. So G best, we would calculate just like we did before. We would just plug in the best values for L and T, and we should get 979 centimeters per second squared. Okay, but to get delta G, we're now going to use this universal formula. So delta G is going to equal the square root of, so how many independent variables are there here with uncertainties? There's 2, right? There's the length and the period. So we're going to have 2 terms under the square root sign. First, we want to take the partial derivative of G with respect to L, right? Holding T constant. And we multiply that by the uncertainty in L and take the square. Then we're going to take the partial derivative of G with respect to T, holding L constant, and multiply that by delta T squared. Okay, so this is the formula we're going to use. So first we need to figure out, well, what are these derivatives that we want to plug in? So the partial derivative of G with respect to L. Oops. So G is linearly proportional to L, as you can see over here. So that's just going to be 4 pi squared over T squared. And the partial derivative of G with respect to T, that's just going to be, so here it's, here we got 4 pi squared L times T to the -2. So to get the derivative, we're going to get a factor of -2, which is going to give us -2 times 4 is -8 pi squared times L. And then we're going to get t to the -3. So t to the third in the denominator. Okay, is that clear to everyone? How we get where we get these derivatives from? Okay, so when we plug these into the formula, then we're going to get the square root of this first derivative is equal to this guy over here. So we get 4 pi squared. And then we're going to take this derivative at the best value of t, of course. So we're going to plug in 1.936 seconds for t, and then this is going to get squared. And then we multiply by delta L. So the uncertainty in L from up here is 0.1 centimeter. So times 0.1 centimeters. This whole thing here, we have to square. Then we're going to get this second term here. So dg dt is equal to this guy here. So we're going to plug in the best values of L and t cubed. That's where we want to evaluate it. So I'm going to take -8 times pi squared times L. So L is going to be 92.95. That's in units of centimeters. I'm going to divide by t cubed. So the best value of t is 1.936 seconds. I need to take the cube of that. And then this whole term here, oh, sorry, I forgot to multiply by the delta t here. So delta t was 0.004. So I'm sorry, this is a little bit sloppy. Oops. But get rid of that bracket here, multiply by 0.004. That has units of seconds. And then I'm going to multiply by, or take the square. Okay, so that's the formula that you would get. And if you plug this all into your calculator, you should see that the uncertainty is going to come out to, again, 4.1 centimeters per second. So we should get, I'm sorry, centimeters per second squared. Okay, so we should get exactly the same thing using both methods. They're mathematically exactly equivalent. So the gravitational constant, again, is just 979 plus or minus 4 centimeters per second squared. Okay. Any questions about that so far? Okay, so that sort of finishes up this section about error propagation. And the rest of these lectures are going to be about curve fitting. And so we'll start with just talking about simple linear fits. And so anytime you do curve fitting, of course, it's important that if you're fitting to some physical equation, you have to make sure that the equation that you're using makes sense for the problem that you're working on, that there's a theoretical reason why you would use this relationship. So for example, if you had 0 husbands yesterday and 1 husband today, then, you know, regardless of what this graph might be showing you, you might question whether this scientist is reaching the correct conclusion that by late next month, you'll have over 4 dozen husbands. Right? Because, you know, if you extrapolate outside the range that you've measured, you might get an erroneous result. Okay, so we're we're going to look at an example of fitting some data to a linear equation. So very often in physics or physical chemistry experiments, you're measuring a certain quantity, we'll call that y, as a function of some variable that you can control in the laboratory, x. And in many simple cases, y is simply a straight line function of x, right? So y equals mx plus b. And so we'll look at an example where that's the case. So if we look at, we'll look at an example where you did a laboratory measurement measuring the compressibility of a gas. So compressibility is a variable called z, and z is defined as pressure times volume over moles times gas constant times temperature. So for an ideal gas, this ratio, you would expect it to equal 1. But if you do this experiment on a real gas, you might get some value other than 1. But you would probably expect, so most gases behave like ideal gases in the limit where pressure goes to 0, in the limit of low pressure. So you would probably expect this z ratio to equal 1 in the limit of low pressure. But if you increase the pressure to some very high value where you would observe non-ideal behavior, then you would expect it to deviate from 1. And so if you look at a limited range of pressures, most often this equation for, so an expansion of z in terms of pressure can be expressed as a linear relationship. So you would get z equals B naught plus B1 times P. So this should give you a straight line with a y-intercept of B naught and a slope of B1 if you plot z as a function of pressure. Okay, so we've measured this data here in lab. You can see that it makes sense. At low pressures, z is close to 1, but at higher pressures, it's deviating. And so if you plot the compressibility factor z as a function of the pressure, then you get these data points here. This is just the data that we showed on the previous slide plotted. And so our goal is to determine these parameters, B naught and B1, because these tell you something about the thermodynamics of the particular gas that you're studying. These are called the first order virial coefficients for this gas. Okay, so how would you determine a fit to the line? Well, you can kind of look at the line or you can kind of look at the data and you could kind of eyeball where the line should be, but that's probably not a very objective way of solving the problem. Because if I told 10 different students, to sort of draw their estimate of what a line should look like going through the data, you'd probably get 10 different lines. So we want an objective way to approach this problem. And the method that we're going to use is called a least squares linear regression. So what does this mean, least squares? Well, it comes from this parameter called chi-squared, which we're going to minimize. So what is chi-squared? Well, chi-squared is just the sum of the squares of the residuals. And what that means is the residual is just the distance of each measured y data point from the linear prediction that you would get from the fit parameters. So in other words, it's the measured quantity y minus mx plus b, right, which you've determined from your fit. And so chi-squared then is defined as the sum of the squares of all of the residuals of the measured data. So you can write it in terms of this expression here. And you can think of that as a function of the fitting parameters m and b. So plugging in the equation for a line here, you would get this expression here. Okay, and so the best fit line then using a least squares method is the one that minimizes the chi-squared value as a function of m and b. So in order to find the minimum of this function, we want to find the value of m and b where chi-squared, where the partial derivative of chi-squared with respect to these two parameters is 0, right? That's where the minimum is going to be located. Okay, so we want to set partial derivative with respect to m holding b constant equals 0, and then also this partial derivative here equal to 0. Okay, so yeah, this chi-squared, we wrote it like this. It's this in terms of a sum over all of the measured data points, x and y. And so how do we take these derivatives? Well, for each term in this summation, we can use the chain rule. So the derivative of a function squared is just 2 times the function times the derivative of the function with respect to x. And so f of x here is just this term in brackets here that gets squared. And so if we take the derivative of chi squared with respect to m using the chain rule, we get one term for each term in the summation. So we can write it as a summation of 2 times f of x, which is this guy in brackets, times the derivative of f of x with respect to x. So in this case, it's going to be minus m is the derivative with respect to x sub I. Oh, I'm sorry. No, I'm sorry. We're taking the derivative with respect to m. So the derivative with respect to m is x sub I. Sorry, I said that incorrectly. Okay, and the derivative with respect to b then is again going to be 2 times f of x times the derivative of this thing in brackets with respect to b. And this derivative, there's a minus sign here, so you just get minus 1. Okay, and if you clean up these expressions, you can write it like this. And we can write this in a little bit simpler form if we make some substitutions. So if we make the substitution, Sx equals the sum of all of the x data points. Sy equals the sum over all of the y data points. Sx squared is the sum over all of the x data points squared. And Sxy is the sum of each x data point multiplied with its respective y data point. Then we can write these expressions without these pesky summation signs, because the summations are included in these variables. And then we just have a function, I'm sorry, we have 2 equations, and we have 2 unknowns, m and b. And these s values you can just calculate from your data. So it's trivial to solve for m and b. And so if you invert these equations, you get these equations for m and b, where this denominator d is given by this expression. So these are just things that you can calculate from your data. So this is a calculation that would involve some work to do by hand, but it's actually straightforward. You can just use these formulas and apply them. Okay, so the next example that we need to work is we're going to calculate the y-intercept, right, B naught, and the slope B1 for the compressibility data that we looked at before by the method of least squares using the equations on the previous slide. Okay, so this is easiest to do in a spreadsheet. So we can go to a spreadsheet. Oh, sorry, let me delete this guy. I'll make this a little bit bigger so it's easier to see. Okay, so this is just the x data and the y data that we had before. And first we need to calculate these quantities, Sx, Sy, Sxy, etc. So the sum over all of the x data points is just equal to sum of this row, or I'm sorry, this column of data here, right? Sy, we can just drag it over to get the sum over this column here. X times y, you can calculate by just taking the x value times its respective y value. And we can drag the formula down to calculate that for each xy pair. X squared is just this column squared. Y squared is this column squared. And I need to copy these formulas. Okay, and then I can also just copy these formulas to get the sum of each of these columns. And then we have these quantities that we need. Okay, so the denominator then, I already went ahead and put in the formula here for this d factor that we saw in the presentation. That is just the number of points, which is 4 times this Sx squared parameter minus the square of Sx. Okay, And then I also plugged in the appropriate formulas for M and B, which are calculated based on these parameters here. And so you see that the slope of the line should be minus 0.0017, and the intercept should be 0.9913. Okay, and this has the intercept is unitless. The slope is going to have units of what? So the y-axis is unitless. The x-axis is in units of atmospheres. So it's going to be 1 over atmosphere. Okay, but you don't have to do it this way. You can actually use built-in features in Excel to do this a little bit quicker. So you can also just plot the data. And so you're going to want to insert a scatter plot, this one here. And I think it chooses some stupid default, which I'm going to get rid of. So I'm going to go to select data. I'm going to remove the whatever it thought I wanted to plot. I'm going to add another data set. I'm going to click here to select the y values that I want to plot. This is the, I'm sorry, the x values that I want to plot. This is the x data. Click here, select the y data. And then I'm going to get a plot. And of course, I want to label my axes. So the vertical axis is compressibility. Have I spelled this right? Stability, which is Z. And the x-axis is going to be pressure. And the units that we had here were atmospheres. Okay. And in order to obtain a linear fit, what you're going to do is left click and go to add trend line. That gives you the best fit line. In order to get the parameters, you want to display the equation on the chart. Okay, and let's see. Okay, that's fine. Okay, so usually there's this problem that Excel doesn't like to display the proper number of significant figures. So if you want to display more digits, you're going to go to Format Trendline Label. I'm going to pick number, but you can pick different formats if you want. And I'll just put more digits so that we can read however many digits we want. So I'll just put 8 digits here. Okay. So now you see that the slope of this line is negative 0.00173. And that matches exactly this value that we calculated over here. And the intercept is 0.99138. That matches exactly this value of B that we calculated. So I just wanted to show you this to show you that you know, these numbers that you obtain using the linear regression in Excel, there's nothing mysterious about it. You could easily calculate these numbers just based on these formulas like we did. Okay, let's go back to this presentation. Okay, so what about the uncertainty in these numbers, right? If you're trying to determine the virial coefficients of a gas, you also want to report the uncertainty if it's based on an experimental measurement. So how do you determine the uncertainty? Well, the equations for that you're going to use, there's this quantity sigma r, which is called the standard deviation of the residuals. And this is just the sum of the squares of the residuals divided by the degrees of freedom, which in this case is n-2, and then you take the square root. And you might notice that when we took the standard deviation of a number that we obtained from an average, right? When we obtained the standard deviation of a set of repeated numbers, the degrees of freedom that we used was n-1, because we had to subtract each number from the mean. And so the mean was 1 degree of freedom, and the rest of the degrees of freedom were n-1. In this case, in order to compute R, we need at least 2 data points to determine a slope and an intercept. And the residuals, you can't start estimating the residuals until you measure the 3rd point. So the degrees of freedom in this case is n-2. Okay. And then the formula for the uncertainty in the slope and the intercept is given by these formulas. So it's just n divided by this quantity d. This quantity d is this guy here. It's this denominator that we saw on the previous slide. And here we have the number of data points. Here we have this sx squared parameter, which is also this parameter defined previously. Okay. Okay, but if you're going to report numbers for the virial coefficients, you're not going to report the standard deviation from your regression. You want to report an uncertainty in terms of a 95% confidence interval. And so the formulas that you're going to use for 95% confidence intervals when you do a linear fit are given here. So the 95% confidence limit for the slope is just going to be this student t factor times the standard deviation for the slope divided by the square root of the number of measurements. 95% confidence interval for B is defined similarly, but you use sigma B. Okay, and in this case, when you go to look up the student t factor, this nu is now going to be n-2, right? Because for the linear fitting parameters, the degrees of freedom is n-2. Oh, I'm sorry. I'm terribly sorry. Yeah, I forgot to, I should have stopped my share. I apologize about that. Stop share. Okay, yeah, my bad. Let me just go back really quickly. So yeah, this is the formula for the standard deviation of the residuals. Here's the formula for standard deviation of the slope and the intercept, right? And this D is just this denominator that we had on this page. It's this guy here. And then Sx squared and N is just the total number of measurements. Sx squared is the sum over all the X's. It's this, oh, sorry, this guy here. And this is how you calculate the standard deviation in the slope and intercept, but the value that you actually want to report is a 95% confidence interval. And the formulas for the 95% confidence intervals are given here. So yeah, the 95% confidence interval for the slope, you use the student t factor times the standard deviation in the slope divided by root n. For the intercept, the formula looks similar, but you use sigma sub b. Okay, and the degrees of freedom that you want to use when you look up this t factor is n-2 when you're doing a linear fit. Okay, any questions? Okay, so now we're going to do another example where we calculate the standard deviations in these virial coefficients that we calculated previously. And we're going to report the corresponding 95% confidence limit. So this time I'm going to change the share correctly. Okay, so I'll go back here. Okay, so basically, in order to calculate this, first we need to calculate the standard deviation of the residuals. So we need to calculate what the residuals are equal to. So over here, I've listed the X values one more time. And we need to calculate the fitted y value for each x point. So we can calculate that just from the equation of a line. So we're going to say y fit equals m times x plus b. Okay, so here are the fitted y values that we get. Oh, something's unhappy. Why is this unhappy? Ah, okay. I need the dollar signs here. Thank you. So I need the dollar signs on M and B. Yeah. And maybe now it will work. Oh no, I did it wrong. Sorry. Should be this one, A14. That's M. Okay, now it's right. Yeah, okay, good. That looks reasonable. Okay, so then now the residuals. So what's the definition of a residual? A residual is just the measured value of y minus the fitted value of y. Okay. And then to calculate the standard deviation of residuals, we need the residual squared. So we can take this number squared. And we can take the sum of the square of the residuals. That's just going to equal the sum of the values in this column. Okay, and then I went ahead and I already entered in the formulas for these standard deviations. So these are just copied from the PowerPoint. So this is just the formula for the standard deviation of the residuals in terms of these quantities here. And then the standard deviation of M and B is given by these formulas here. You can take a look for yourself, make sure I did it right. And then the 95% confidence intervals. So the first thing that we want to do is we want to look up which student T factor to use. So we're going to go to the table. Oops. And it's way back here somewhere. Yeah, so here's the student T factor table. So the number of measurements that we made was 4. And the student T factor we want to use is n minus 2. So in this case, it's 2. So the T factor from this table is going to be 4.3. Okay. So if I go back to my spreadsheet, so I use 4.3. This is the student T factor times B14. That's the standard deviation in n divided by the square root of the number of measurements. Okay, so the 95% confidence interval in the slope is going to be 0.0038, and in the intercept is 0.01. Okay, so I'll go back here. Okay, and so we're going to get, let's see, if we wanted to report these numbers, then we would write this as, so the B1 coefficient was the slope. So this is minus 0.0017 plus or minus 0.0004. And this had units of reciprocal atmospheres. Or if you wanted to write that in a slightly neater format, you could use an exponent. So you could say it's 1.7, I'm sorry, minus 1.7 plus or minus 0.4 times 10 to the minus 3. per atmosphere. Okay, and then the B Naught coefficient, the way that we could report that is it's equal to 0.99 plus or minus 0.01. And this is unitless. Okay, and then the problem asked us to specify that this is 95% confidence interval with n equals 4. Okay, oops. Okay, so one more topic for today, and that's the linear correlation coefficient. So there's a coefficient, it's called R. It's calculated according to this formula where dx squared, dy squared, and dxy are given by these expressions here. And the correlation coefficient is basically a quantitative measure of the extent to which x and y are linearly related to one another. So if x and y were completely uncorrelated, completely random, then you would expect to obtain a value of R that's close to 0. If they're very, very strongly linearly correlated, then R would be close to plus or minus 1. And R would be plus 1 if the slope is positive. R would be minus 1 if they're perfectly correlated with a negative slope. Okay, so we can also use this formula to calculate the correlation coefficient in our spreadsheet. So let's do that. And basically, I went ahead and did it for you. So first you calculate these dx squared, dy squared, and dxy values. These are just calculated from these values that we had up here. So you have the sum of x squared, and number of points. And so here's what you get for dx squared. For dy squared, it's just calculated according to this formula. You can check it for yourself if you like. So this spreadsheet, I'm sorry, this Excel file is going to be on the Blackboard, so you can take a look if you want later. And dxy is calculated according to this formula. And so the correlation coefficient is just, let's see, dxy divided by the square root of dx squared and dy squared. Okay, so in this case, we get a negative number, which makes sense because the slope of this plot is negative. And it's close to 1, which means that the measured data is very approximately linear, right? There's a very strong negative correlation between the x and y data points. Okay, you can also get Excel to show you at least the square of the R coefficient, which is actually more commonly reported than R. And the square, if you just calculate the square of this number, should be 0.979. And let me just redo this. So the way that you get there, or the easiest way to get Excel to show you this, is you just do add a trend line again. The default is a linear trend line. I'm going to tell it again to display the equation on the chart. This time I'm going to say also display the R squared value on the chart. And then it displays this R squared value, 0.9796. And if I did this correctly, it should exactly match this value that we calculated by the long way. Okay, it's also possible to get the standard deviations using built-in functionality of Excel. It's a little bit tricky, but the function that you use is called lineest. So I believe on newer versions of Excel, it's a little bit easier to do. On my version that I'm using, I haven't updated my Excel recently. So basically the way I have to do this is select a range of cells. Then I hit equals lineest. And then it helps you out. It tells you what it wants. So first it wants the known y's. So I'm going to select the y values that we're using, then the known x's. And then there are two options. If I choose false, then it sets the intercept equal to 0. If it's true, then it calculates an intercept. So I want true because I want to calculate what the intercept is. And then I want to return additional regression statistics. So I hit again here, true. And then in my case, I have to hit control command return, or control or I'm sorry, Shift Control Enter. Okay, that didn't work. What am I doing wrong? Let me try this one more time. Okay, that time it worked. Okay, I believe in the newer version of Excel, you don't have to hit Command Shift Enter. You can just enter line est, and it'll come up with all these parameters. Okay, so now it's displayed a bunch of numbers. So how do we interpret these numbers? Well, you can look in basically the Excel documentation and it'll tell you what they mean. But I can tell you right now, the first column here, I'm sorry, the first row here is the slope and the intercept, right? Which you can tell by comparing to the numbers that we calculated. The second row here, whoops. Okay, the second row here is the standard deviations in the slope and intercept, right? So it should match this number here and this number here, which it does. So we calculated it correctly. And then this next value down here is the R squared value, which should match this number here. So if you don't want to go through all these calculations, like is shown in the spreadsheet, you can use this line est command. Okay, any questions? Yeah, I should mention, I'm not aware of a way in Excel to immediately get the 95% confidence intervals. So that you do still need to calculate by hand. So you would take, if you're reporting these numbers, these slope and intercept, you would take the values reported here, plus or minus 95% confidence intervals, which you would then have to calculate from the standard deviations using the formula in the presentation. Okay, any questions? Okay, I believe that is everything for today. So if there's no questions, we can finish a little bit early. And next time we're going to talk about, oh, there is a question. Oh, whoops. Okay, basically it doesn't matter because, wait, you should be able to see. That was earlier. Oh, okay, never mind. You can get 95 in Excel. Does that mean I should update to the new version? Okay, well, yeah, I need to update my software. But it still works if you do it correctly with the old version. Okay, so I will see everyone then again on Tuesday, and then we'll finish up with these lectures next week. So thank you very much and have a good evening.